Today, let's look at the problem network of schools. So in this problem, we are given a few schools, and each school can send a software to some other school. So what this basically means is that we're basically given a directed graph, and we have to perform two tasks. For the first task, we have to find the minimum number of schools that we must send a copy of this new software to, so then every other school can also receive this software. And so to do that, we will use BFS and basically get a group of schools that are connected to each other and find another group, and basically count that amount of groups. And then for subtask B, we can, so basically what we want to do in subtask B is to make it so that this whole graph all have loops. And so what that means is that this whole graph is strongly connected, meaning that any pairs of nodes can be reached in this graph. And so first we will deal with the first subtask. Here's the code. We will use just one BFS for the first one. After writing the graph, I will use this group array to keep track of which group this current node or this current school is in. And so if this school isn't in a group yet, then we will use BFS on this current school. And so here's the first BFS. It is basically a normal BFS, and we're just reading this, and we're setting whatever this school is connected to. So everything that is inside this queue will be all connected to this current school, the source. And so we will set all of the group to this C, which I defined from outside. So this won't change every time when we're using this loop, but it will change from using the main function. So this is basically normal BFS, but every time we're reading a school, we will set it to have the same group as the current school. So this will go on for all of the schools that aren't in a group yet, and we'll be able to get the number of groups there are by keeping track of the visited amount of groups. So using this, we can check how many distinct type of groups there are, and that is basically the answer for the first subtask. For the second subtask, we will have to use a few tricks or algorithms. First, we need to get all the strongly connected components in this graph, and strongly connected components are just a subgraph that is to have a cycle, so you can basically reach any pair of nodes in that subgraph. For example, let's look at this example network. So this is basically what the example network is. Here we can say that just 1, 2, and 5 are strongly connected because they form this cycle which can make us reach any two pairs of school. So here 1, 4, and 2 are not connected because they don't form a cycle, because we can start at a 1, go to 2, go to 4, but we cannot reach 1 from 4 because there's no cycles in this graph. So we will only find graphs that contain a full cycle. So to do that, we will use DFS. And first, I will check for all of the nodes that we didn't visit yet. We will use DFS on that. And this is the first DFS. Here we'll use stack to keep track of the order in which we traverse the graph. So then later on we can go in the reverse order, and after we finish encountering cycles, we will set those nodes to visited, so then we won't visit those again, and this will help us give us the strongly connected components. And this first DFS is basically pretty much a normal DFS. You will set this current node to visited, and then check for all of the other nodes that are connected to this current node and also not visited yet. Then we'll use DFS on that. And finally, after we use the DFS, we will push this current node into a stack. And after we do that, we will reset this group to 0 again, because here we're using another type of group. Here we're not using that simple group. We are grouping these schools by their strongly connected components. So we will start at the top of the stack. So basically this is in the reverse order, since we first traverse all the way down to the end, and then we push this back one by one. So what will be at the top will be at more at the beginning of this traversal. So here we will go through the stack, get the top, and pop it. Then we will check if this current U is already in a group. If it's not in a group, then we will use another DFS on this to set it to a group. And here I also used C to keep track of which group we're in. And in this DFS too, it's also basically the same as a normal DFS, but here we don't look at the visited, we can look at the group right away. Because if we didn't visit it, then the group will stay at 0, and we will be able to visit that using DFS. So we change whatever group this U is in to C. This is how we find the number of groups there are for our. So basically, this C will count how much strongly connected components there are in this graph. If C is equal to 1, this means that this whole graph is connected, is strongly connected. So we can return 0, meaning that we don't have to add any more edges because they are already strongly connected. You can reach any two nodes already. So if it's not strongly connected yet, we will try to find how much we have to find how many edges we need to add, so then it will become strongly connected for this whole graph. And to do that, we will use BFS again. But here, what this BFS does is it will find the number of find the in degree and the out degrees of each strongly connected components. So here we're basically treating the strongly connected components as one node, and then performing the graph search on that to find the in degrees and out degrees of these strongly connected components. So for example, here we will be considering this 1, 2, and 5 as one component because they're strongly connected, and then 3 will be one component by itself, and 4 will be one component by itself. So we can say that this will become basically A will represent this graph, this subgraph, or this strongly connected component, and then we can say B will represent our this 3 because it's just a strongly connected component by itself, and then C will represent this 4 over here. So then this BFS will do later on will take a look at the edges that connect different components. So we can ignore all of these edges that are inside one component because it's all considered as one. So we should only look at edges that connect to different components. So here we can see that this component, this 1, 2, and 5 is connected to 4. So we basically have an edge from A to C. And then here we can see that 1, 2, and 5 is also connected to 3. And 3 and this 1, 2, and 5 are from different components. So then we can say that A also is connected to B. So this is what we're actually searching for. We're actually looking at this small graph here. And then to get the final number of edges that we need to add, we will get the maximum of the total number of nodes that doesn't have any in degree, and total number of nodes that doesn't have any out degree. So we will find the maximum between those two, and here we can see that the maximum here will be 2 because A doesn't have any out degrees, but then so A has only out degrees and does not have any in degrees, and here B only has one in degree and does not have any out degrees because it's not connected to any other node. And this is the same with C. C is only connected from A, but it's not connected to anything, so it has an out degree of 0 as well. So these two will be the maximum because it's the total number of nodes that does not have the total number of nodes that don't have any out degree. And to get the number of out degrees, we will use this BFS. It's so here it's basically the same thing as a normal BFS, but every time we will change the out degree and in degrees of these two different groups. So first we have to make sure that they're in two different groups, because if they're in the same group, we shouldn't change anything, because there's no need to bother about things that are inside one component. So there should be this U and V should be in different groups, and if they are in different group, this means that this U is connected to V, which means that this component GU is connected to GV, and so this means that this component that U is in has at least one out degree, and here we will just mind about one out degree. We don't have to mind about multiple ones, because we're only looking for the ones that does not have out degrees. And also this is the same with the in degrees, but here this is GV that is having an in degree, because it's receiving this from U. So V is receiving a software from U, then that means it's an in degree for V. Then we will basically check if it's not visited and push this into the queue as a normal BFS. So after this finish, we also have to make sure that we will loop through all of the components in here, because some of them might not be connected at all. Then we wouldn't visit that yet, so we have to visit those as well. And finally, we will get the total number of out and in degrees. So just loop through all of the groups from 1 to n. Here we can guarantee that the maximum amount of group is n, because the most amount of groups you can have is when you don't have any connected edges, or when you don't have any strongly connected components. Then that means every node is by itself, and so the maximum is only n. So here we're adding the total number of in degrees and total number of out degrees, or you can think of this as the total number of components that have an in degree and the total number of components that have at least one out degree. So to get the number of components that do not have any in degree, we will subtract this total number of in degrees from our number of components. And also to get the total number of components that do not have out degrees, we will subtract the total number of components that have out degrees from our total number of components. So we'll get the maximum between those two, because we're basically looking to form a cycle here. And then after that, you'll get the result for a subtask B.